We will now discuss a few of the practical realities of plotting production data in order to obtain accurate decline curves. We may divide our discussion into three principal areas. First, how we distinguish changes in the production response of the reservoir from changes in wellbore conditions or operating practices. Second, how production data is prepared for extrapolation. And third, how we incorporate changes in operating practices, for example, the addition of a new well to production or the installation of artificial lift, into our decline curve analysis. Let's begin with the first area. You will remember that decline curves are intended to represent the behavior of the reservoir. Therefore, the data used in developing them should not include wellbore interference, failure of lifting equipment, or operating practices which are temporary in nature. To project data into the future that reflect, for example, a poorly operating pump that will soon be repaired, a damaged formation which will soon be stimulated, or the low production period during a well workover, will not give us an accurate decline curve. It is the engineer's job, then, to review the raw production data in order to distinguish reservoir performance from that performance caused by transient operating practices, and by practicing good judgment, to restate the data for decline curve analysis. Once this is done, the data should accurately reflect the performance of the reservoir for this well or field. Our second concern is the way in which raw data is handled.
Let's use the raw production data shown here to analyze a particular well's decline performance over a 6-month period of time. We have values of 15,000 barrels for the first month, 9,500 for the second, 16,200 for the third, and so on. Because wells are seldom produced in the same way each day or month, the plot of rate versus time for these discrete points will show some scatter, as seen here. We may join the points together, and in doing so, we obtain a sawtoothed line. In order to obtain a single straight line on semi-log paper that we expect for the rate-time curve, we have three choices. We may eyeball the data, that is, on a somewhat arbitrary basis, draw the best straight line that we see through the points. Although somewhat inaccurate, this procedure is often used. Alternatively, we may smooth the data by using a method of averages. Finally, as a third alternative, we may use one of several methods to find the equation of the straight line that best fits the given data points. The method of eyeballing is one that we all understand, so let's spend a few minutes on the ways in which data may be smoothed, or alternatively, on how a best straight line fit is calculated. Let's begin with the smoothing of data. One way of smoothing this data is to add the production for a 3-month period, that is quarterly, and then plot the 3-month production at the midpoint of the quarter. The plot point then for the first 3 months would be at the middle of the second month, and the plot point for the second quarter would be at the middle of the 5th month, and so on. The best straight line is then drawn through the points, and by dividing the quarterly production rate by 3 for any given month, we have an average value of the monthly production rate. There is a second method for averaging data, which is even more widely used. It is referred to as the moving average. In this method, we must first select the number of points over which we would like to carry out a moving average. In looking at our data points, we realize that they are cyclical, with a period of about 3 months. So we shall assume a 3-point moving average. The procedure is quite straightforward. We add the production for the first, second, and third months, divide the sum by 3, and plot the resulting value at the second month. Then we take the production for the second, third, and fourth months, add them together, divide by 3, and plot the resulting average at the third month. This procedure is continued until we run out of 3-month periods of production, straddling the plot point. In this case, then, we will plot a point at the 4th month, and then one at the 5th month. With these new data points, we have smoothed out the original data, and can now draw a single straight line through the averaged data points. In doing so, we remember that the best fit is where the area above the line that we draw is equal to the area below the line. The third method for obtaining the required decline curve through the scattered points uses methods of graphical mechanics to find a best straight line equation. In order of increasing complexity, these best fit methods include slope-intercept, selected points, the method of averages, the methods of moments, and the method of least squares. Each of these methods is discussed in your workbook. In order to show how one such method is used, we shall apply the method of averages to our sample data points. We know that our basic rate-time equation should have the form shown here. We may rewrite it by taking the natural logarithm of each side. The rewritten equation is a straight line on semilog paper. In order to obtain a unique line, we must calculate values for the two unknowns by writing two equations and solving for the two unknowns. To do this using the method of averages, we divide the data points into two sets, usually 3 to 6 points each. The data sets are selected at each end of the information provided. The data set at one end provides one equation, and the data set at the other end provides the second equation. For our 6 months of data, each set will consist of 3 months. Set 1 will consist of the first 3 months, and set 2 of the latter 3 months. If we write the equation for each month and sum the 3 points for each set, we obtain the two equations shown here. This allows us to solve for Q sub I and D, and then to write our specific equation for Q sub T in terms of time, T. It is this specific equation, then, that we use to extrapolate our data into the future.
Now that we know that we must analyze production data before accepting its validity, and that valid data points must be smooth before calculating the best straight line, we should say a few words about how to incorporate changes in operating practices into our decline curve analysis. Let's look at a few specific examples.
The addition of new wells will cause an increase in monthly production for a lease and add an upward swing in our decline curve for the total lease. The best way to incorporate this effect is to plot production rate on a per-well basis for the lease. Well stimulation may also cause an increase in production rate, but will not necessarily affect the ultimate reserves that are to be produced from the well. The increase in production rate early in the life of the field should be included in the production data, since it will influence the decline rate and the overall economics. The addition of artificial lift to an oil well will cause an increase in production rate for a period of time, and an increase in producible reserves over that which would be realized from natural flow alone. The introduction of enhanced recovery methods, such as water flooding or CO2 injection to a reservoir, should increase the ultimate producible reserves, as well as the production rate. These effects should be incorporated into the decline curve, but guidance should be sought from suitable reservoir engineering studies. A change in product value or operating costs will change the economic limit of production, and thus the crude reserves. A review of the economic limit then should be made annually. Fractured reservoirs provide a special problem for decline curve analysis. During the early stages of production in these reservoirs, a well will produce at a reasonably high rate while the fracture zones are being depleted. The production rate will drop off substantially as the rate of production from the tighter matrix into the open fractures begins to control production rate. The time at which the production will drop from one level to another and the rate of production after the drop has occurred are usually not known.
Estimating production from fractured reservoirs during the early stages of production, then, is similar to the problem of estimating future production from a well which is being restrained at a constant production level by proration or engineering limits. Well tests are often helpful, but most experienced engineers will look to nearby wells or comparable fields in order to obtain an estimate of what the ultimate decline rate might be. There are many other examples where care must be taken during the extrapolation of decline curves. You've probably already thought of some. For now, though, would you please stop the player and work problems 7.7, 7.8 in your workbook. We now have a good understanding of the sequence of events that should occur in order to prepare a proper decline curve. Let's take a moment to summarize.
First, we review the data and discard non-performance or faulty performance data. Second, we plot the data on both the rate time and rate cumulative production curves. The rate time curve is plotted on semi-log paper, and the rate cumulative production on linear coordinate paper. Next, we smooth the data, or find the best straight line for the points given, and calculate the economic limit production rate. Before proceeding further, we check to be sure that no new operating practice has been recently imposed or will be imposed in the near future. Satisfying ourselves on this point, we are then free to draw the straight lines on the two plots. We remember to spread out the production near the end of the life of the well, because the constant percentage decline curve tends to be conservative in this region. We now have our production rate versus time profile and our reserves. Before committing ourselves to these values, we must check to see if they are reasonable.
To do this, we see whether they compare with the recoverable reserves calculated on a volumetric basis. Then see if they compare favorably with other wells in the area. And finally, if the reserves estimated are too high or the production life too long, we check to be sure that there are no infill locations which could be drilled to produce these large reserves. If so, we must cut back on the reserves of this well. Let's now take a moment to look at some of the characteristics of gas well reserves and decline histories.
We know that for a fixed volume gas reservoir, that is, where there is no water encroachment, the plot of average reservoir pressure over Z, the gas compressibility factor at that pressure, versus G sub P, the cumulative gas produced, yields a straight line on linear paper. As we see here, the endpoints of the line are the original reservoir pressure, P sub I, divided by its compressibility factor at zero cumulative production, and the original gas in place at zero pressure. A gas well will no longer flow when the average reservoir pressure drops to a value equal to the pressure in the well bore imposed by the back pressure. The well bore back pressure, P sub WF, as we see here, is the sum of the back pressure imposed by the sales line at the surface, plus the pressure loss that occurs in the gathering system and the tubing. Thus, for example, if the sales line back pressure is 600 psi, the gathering system pressure loss 25 psi, and the tubing pressure loss 50 psi, the wellbore pressure imposed by the accumulation of these three values will be 675 psi. When the average reservoir pressure falls to this value, no further flow will occur. This no-flow point should not be confused with the economic limit production rate. If, for this example, the original reservoir pressure had been 1700 psi and its Z value 0.87, then the end point of the curve, as shown here, would have been 1,954. The other end point would have been the original gas in place. In this case, it is 10.5 billion cubic feet. To determine the cumulative production at the no-flow average reservoir pressure, we divide the value of pressure, that is 675 psi, by its Z value, in this case 0.92, and obtain a value on the vertical axis of 733.7. Moving horizontally to the inventory line and then down, we see that the reserves that could be produced at this terminal pressure would be 6.54 billion cubic feet. If we were to install a compressor at the point of sale with a 4-to-1 compression ratio, the minimum suction pressure would be 150 psi. If to this suction pressure we add the gathering system pressure loss and the tubing pressure loss, we would obtain a no-flow wellbore pressure of 225 psi. Referring once again to our inventory curve, we find that the no-flow condition would occur in this case at a point on the vertical axis equal to 225 divided by its Z value, 0.96, or 234.4. This yields a producible reserves of 9.24 billion cubic feet. The difference between the two cumulative productions, approximately 2.7 billion cubic feet, is obtained by the installation of compression. An economic analysis would have to be made to determine whether the value of the additional reserves produced exceeds the capital and operating costs of the compressor.
The economic limit production rate, as we learned earlier, is the rate at which the value of production is equal to the cost of producing the well. Once we know this flow rate, we may use the well's deliverability curves and the flowing wellbore pressure to determine the average reservoir pressure at the economic limit. It is then a simple matter to find the P over Z value for this average reservoir pressure. Then, using the inventory curve, we may estimate the total reserves that would be produced at the economic limit. A full discussion of gas well deliverability curves is given in the video library program on gas well testing. The reserves information that you calculate for a well or field will be used by a number of people in your company to prepare a schedule of total production by month or year for the division. Your reservoir engineers may review the data to see which wells might be candidates for stimulation or enhanced recovery. Your accountants will want the information to calculate cost depletion, and your evaluation engineer will use the information to calculate the value of the reserves for submission to banks for loan purposes and perhaps to shareholders on annual reports to show the value of your company's major assets. You might even find the exploration specialist responsible for discovering the field in the first place taking a look at these values from time to time to see just how much money he made for the company. We should remind you that what we said at the beginning of this module, namely that production decline curves enable us to extrapolate historical production data into the future. It is possible that they may contain substantial error, especially for extrapolation far into the future. For this reason, we recommend that they be reviewed from time to time, annually if possible, and updated as new information becomes available. For the next few minutes, let's listen to an interview Dave Donahue conducted with Forrest Garb, an independent reservoir engineer and president of H.J. Gruey & Associates in Dallas. We'll be talking about many of the ideas presented earlier in this module.
Forrest, the viewers of this program have spent the last hour or more learning about decline curves. You're a reservoir engineer that has been looking at decline curves for a good number of years. I wonder if you could share some of your insights with them, first generally about decline curves, and then later we'll come back and talk about the specifics of their preparation and their analysis later on.
Dave, the so-called decline curves are merely graphical representations of established trends, and man, since time began, has used the past to indicate the future. The actual performance of a well, a lease, or a reservoir is the proof of the pudding. It's the real indication of the capability that entity has to produce hydrocarbons. Once we have established a trend, regardless of what data we are plotting, an engineer has some confidence in the extrapolation of that trend, that such an extrapolation is a representation of its future. Extrapolating a decline curve or a performance trend is a little like shooting a firearm. If the history we have to extrapolate is very short, it's much like shooting a pistol. Our line of sight is short, our accuracy is questionable, we may miss the target. If we have a long producing history, it is more like shooting a rifle. Our line of sight is longer, we have better confidence in our data, and we can extrapolate it with a bit more accuracy and have, again, a higher confidence level in the reserve that we conclude from that extrapolation.
Of course, the first step in preparing our performance curve is to collect the data and assemble that so it can begin, you can begin the analysis. How do you go about collecting and analyzing the data?
Of course, producing oil companies usually have their production recorded in data processing equipment. These data frequently are available to you in magnetic tape. In smaller offices, they may exist in production ledgers where the data have been recorded by hand, or in the instances of commercial services such as Dwight's and PI, one can order the data and order that data in various formats. They can come to you in a ledger form, printed on data processing equipment, or they may come to you in magnetic tape, or even now in automatic printouts in the forms of plots. Of course, plotted data come to you in their raw form, and they do not give you the privilege of working with the data prior to being influenced by the visual representation of those data. Normally, once the data are in the hands of an engineer, it becomes his subjective analysis that determines the value of the data in the final representation. He must smooth the data if it's erratic. He must eliminate from the data those perturbations that he feels are non-representative of that producing entity's real performance capability. For instance, if due to the rupture of a gathering system line there has been the need to shut in a field or a well, that has to be accounted for and not let such perturbation influence a projection. On the other hand, if the data have been recorded as sales rather than as production, then the information that you receive as an engineer will reflect how frequently oil was sold, and it may not be a very accurate representation of how that oil was produced. This is particularly true in long-lived and low-productivity fields, reservoirs, or wells. Once the data are filtered and smoothed to remove any impact of non-capacity related information, then the normal procedure is to make a graphical representation of these data so that they may be analyzed for projections. The projections are usually done in one of two ways. They may be mathematically analyzed either through computers or equations to define the equation that best represents the observed, filtered information. Once the equation for that line has been determined, it can then be computed into the future to predict the future trend or performance. A second very common procedure for extrapolation is merely for the engineer to put his best estimate of a line through the data points. I believe it would serve our purpose to touch on the kinds of data that are frequently plotted and extrapolated. Of course, the most common extrapolation is a rate time curve of the product being sold. In the case of oil, that would be oil. In the case of gas, it might be gas and its associated liquids. Nevertheless, the log of the rate of production is plotted versus the time of production for analysis. In the case of natural gas wells, rate or log rate versus time is also frequently plotted, but a more frequent technique is to plot the pressure divided by gas deviation factor at that pressure, commonly referred to as P over Z, is plotted versus the cumulative production to that pressure point. By analogy, this is similar to saying if you have 30 pounds of air in your tire and you let 1 cubic foot of air out of your tire, and the pressure is now 15 pounds, it therefore follows that if you let another 15 pounds of air out of your tire, there would have been 2 cubic feet of air to vent. You therefore have a means for estimating the gas that was initially in the reservoir by observing the pressure versus cumulative performance from the reservoir. Water-oil ratio is another trend that is frequently plotted for extrapolation. Extrapolation of the water-oil ratio will indicate the amount of oil that may be extracted from a producing entity at the time when the amount of water you produce renders the operation non-economic. Water-oil ratio is frequently plotted versus cumulative production, or may be plotted versus time in some instances. Gas-oil ratio is often a value that is extrapolated to estimate a limit of productivity. In all instances, the terminal point for an extrapolation is usually defined as the economic limit. In the case of producing rate curves, it is that amount of hydrocarbons that are being produced which constitute a break-even point with your operating costs. In the case of water flood or water drive reservoirs, it may be the water-oil ratio that again renders the operation sub-economic. I believe it would serve to concentrate on the types of curves that we frequently extrapolate, and the most frequent one would be the log rate of productivity or deliverability versus time. The log rate of production versus time usually exhibits a mathematical shape that is termed exponential or constant percentage, which is a straight line on semi-logarithmic paper. Hyperbolic, which is a hyperbola but appears as a curved line on log rate versus time curve, and a Dukes mixture called a harmonic curve, which is a difficult curve to analyze but sometimes does exist. Exponential decline, or constant percentage decline as it's sometimes referred to, almost always becomes a fundamental segment of a decline curve analysis. In high permeability or good deliverability reservoirs, an exponential decline will make itself evident as a straight line on semi-log paper early in the life of a reservoir. And this makes extrapolation of such performance curves reasonably accurate tools for estimating reserves rather early in the life of a field or well, perhaps as short as 1 or 2 years. However, since 1979, the exploration and development of lower permeability reservoirs has made hyperbolic performance more prevalent in the normal data we observe, particularly for the early years in the production of the low permeability reservoir. In such instances, the data can be analyzed mathematically to define the equation for the hyperbola, and this equation can be solved in order to project the future performance of the producing entity. This, however, has to be treated with caution, for the equation of a hyperbola flattens continuously and asymptotically approaches a horizontal line. Such treatment would obviously solve the energy crisis if applied to all the reserves in the world. You therefore must, as an engineer, observe by analogy the minimum decline rate extant in the area and use this as a limit to your hyperbola never allowing it to flatten beyond that which you as an engineer would assume to be in effect for the reservoir fluids, the reservoir rock, and the area in which you are working.
Forrest, once you have then the reserves estimation by your projection of your decline curve, there must be something further you do to analyze whether it's reasonable or not.
Yes, Dave, there are several procedures that must be looked at. First, one must look at the nature of the data itself. Were the data consistent? Was the line that you evolved from your filtered data in good agreement with each successive point, or was there a lot of scatter? If the data that you have applied for extrapolation render a good least squares fit regression, you can extrapolate with reasonable confidence that your answer is a good approximation of your reserve. If the data were highly scattered and very erratic after your very best filtering, you come away with a reserve estimate you have less confidence in. So the first thing that you would want to do is to confirm that you have consistency in your data. Secondly, then, you would analyze the operating procedures to identify that there will be no changes in these operating procedures during the projected life. For example, the performance curve you have extrapolated represents a certain energy in the reservoir that is yielding that performance curve. If you know that there will be offset drilling or infill drilling, which will not only rob or steal portions of this energy, then you must accordingly adjust your reserve estimates. In addition, if you are aware that there are workover programs that include perhaps opening more of the zone, deeper penetrations, well rehabilitation, installation of larger pumping equipment, or any operational procedure that will be reflected in your rate time curve, pending in the program for your company, these facts must be included in your prediction of reserves. Obviously, secondary recovery or enhanced oil recovery procedures must be considered as not included in historic performance curves that represent energies prior to any enhancement operations. In addition to these cautions, there are two additional cautions in using decline curves exclusively. In the case of water drive reservoirs, or partial water drive reservoirs, a well which has exhibited a performance may cease to exist in as short a period as a few days as the waterfront hits the well. There are other calculation techniques for determining whether or not water influx is contributing to a performance analysis. Failure to study this factor, however, can yield very optimistic estimates of reserves. A second case is in superpressured gas reservoirs. In this instance, where a reservoir has a pressure in excess of the hydrostatic gradient, the overburden, or the soil above the reservoir, is floating on the pressure contained by the reservoir rather than resting on the grains of sand of the reservoir rock. Therefore, as we produce this reservoir, there will be a relaxation of the overburden until such time as the sand grains take up the load. During this relaxation period, the overburden supplies energy to the reservoir. After relaxation, when the sand grains take up the load, the contribution from the overburden is greatly diminished. Correspondingly, there will be a P over Z curve that exhibits two slopes. Prior to relaxation of the overburden, its slope will be shallow, and there will be a knee bending downward when relaxation occurs, and the slope thereafter will be far steeper. Again, there are correction calculations which will render a single P over Z curve corrected for the overburden. But if one does not make such corrections, again, in the early life of the reservoir, he will extrapolate to a very optimistic reserve.
We want to thank Forrest for his contribution to our study of decline performance. His comments help to put into perspective much of the information we've been discussing. We wish you every success in your application of what you have learned in this series.
This program has been sponsored in part by the following companies: Agip, Aramco, City Service, Dome Petroleum Limited, Gulf Oil Corporation, Mobil Oil Corporation, Phillips Petroleum Company, Standard Oil of California, Texaco Incorporated. IHRDC and these companies, by their sponsorship, do not in any way guarantee or represent the accuracy of the content or methods contained herein. The user hereby agrees to hold IHRDC and the sponsors jointly and severally harmless from any and all damages, including legal expenses, which may arise from the use of this program. No portion of this videotape may be reproduced without the permission of IHRDC.